Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schrenkleberg.
And this is Kirk Bray.
Hey, Kirk. We were just chatting, and I said, wait a minute. It's like we almost always do. Let's hit record. We may have talked about this at one point or another, at one fashion or another, but I think we both have learned a lot over the years, and it's worth coming back to, is that you run into an organization that says, yeah, we'd like to give HALT a try. And let's get Kirk in here. He's the HALT guy. Mm-hmm. He wrote the book on it. And let's see if we get it. And you and I have both run into places where they go, well, of course it failed. You overstressed it, and they just don't get the concept and everything else.
Right.
But how do you go to an organization, is the basic question here, and say, hey, this actually works?
Right.
And you were just outlining one. I go, yeah, I've used that before. It works great.
Right.
Although I did have one person sitting there with his arms crossed going, well,
yeah, you always have that in your audience.
Yeah.
And there's two conditions that there are companies developing a new product. That's one path, mm-hmm. and that they don't know anything about the future of their.
They know a whole lot, but they
know
a whole
everything. Lot from a predecessor product or maybe another product.
Well,
okay.
It's not all brand new technology, but it's a new invention. Right. It's a new vendor. It's a new something. I would say that there's things that they're uncertain about, and they may well be surprised what they find, but it's not that they know nothing.
Right. It's not that they know nothing. They've done some analysis. They've done some design reviews. They've looked at this. They don't. And again, what we're looking for in the testing is to find things that we didn't quite expect or were overlooked or didn't know about. Obviously, you wouldn't put it in the machine or the design if you did know it was going to be a marginal condition.
Yeah, or just would fail outright at 1 degree above your spec, stuff like that. Or failed. I had one that failed and it shorted the battery out and it just smoked. It didn't catch on fire, but it drained these two AA batteries really fast.
Right. But you don't always get the destruct level. You don't always get the actual catastrophic.
But there's so much fun when you get it. It's worth doing HALT just for that.
Those are the exciting ones.
That's right. And then you can do it again and get a camera on it, get your video of it going, exploding and stuff.
Well, yeah, you don't usually need to blow up too many of them, Once you find that, you start investigating, but and find the root cause.
But all right, so you got 10 folks in this design team, and they go, we already have it in the field, That's the other scenarios. They got a product out there.
Well, that occurred with my first HALT client way back in the early
in the
1996 or something. I can't remember exactly, but it was a power supply company. And, the thing that blew up in the HALT chamber was a 500 volt, 150 amp switch, a diode. I mean, it did. It blew up the package, and it was really. And going to the manager of the product, he says, "Wait, we don't have. They've been shipping it for 2 years." He says, "We don't have anything coming back from the field that has a blown up rectifier." Like that. He says they never come with a split package open, because it was about a 2 inch by 3 inch, 1 inch high. It was a large device because it carried so much power. And so, I had to probably agree with him. Well, that's probably true. But the fact is that was limiting the ability to screen with thermal cycling because it blew up at the low one at 35C, which was I think 40C or something. And it was a wide distribution between the 3 samples that we tested, one going to 90C. So there was, between 45 and 90C. So this is where statistics won't help you, but common sense will. And if you see a large distribution in a particular limit, then you probably have a wide distribution in the larger thousand population or hundred. And that's where the tails of strength go into the limited tails of most harsh stress. So whether when we changed that part from 100 amp to 150 amp, we got all three samples that we had at the same model to go all to 90C before they had an issue. And so that was enough margin, and the cold was not a problem, that we could swing as we try in halves. Usually the goal, as Greg Hobbs would always kind of say, is 100-degree centigrade swing between hot and cold. And we achieved that. So they started immediately after that. We developed a screen of about an hour and a half long, and lo and behold, the failure rate dropped, or warranty return rate dropped from 5% to 0.5%. And that was all they needed, even though I had to overcome the fact that, this did not fail the way we did in HALT. And whether that extra margin on that particular switch going from 100 amp to 150 amp was a real benefit, or whether the screening, the half screening, was what was helping to prevent
that's the hard
the manufacturing.
One of the hard parts, and it takes really good failure analysis, and having something blow up makes that more difficult sometimes, because you don't know if you found a technical limit and you just blew past it, or like you outlined, is that it indicated there's a lot of variability here. And at lower voltages, when you're not over stressing it and over temperature and all the other stuff, voltage and current do cause damage, just much slower. So it's if that was due to electromigration or an overheat, thinning out of a trace, and then it, because of such current flow, that it thins it out and then it heats up and then it causes problems. And, there's so many different mechanisms that could be at play. I always find that if you can get a good failure that, it's like, well, we never seen these in the field. It's like, well, this is this is the end result of a accumulated damage, and you get a degraded performance much earlier than it failing catastrophically. If you have a good mechanism that you can point to and have evidence for. So some people will believe, if they have a good culture around doing decent failure analysis, and that's another one to overcome. It might be not that they don't believe HALT, is they just don't believe failure analysis. They say, well, we'll just shotgun this. Let's just swap these parts out and then we're good. Let's blame the supplier. That's another issue. But so part of it, I think there's two tracks to, and there may be more tracks to proving HALT works. One is, I think you were talking about the first time, is you have an existing product, you have some problems in the field, and you can go to HALT and say, here, it took me a day or 2 days, and I had found that problem. And here it is. And then there's other ones like a new product. And I had the classic example I've had, and I know I've told the story before, is where that battery shorted out. And they immediately fixed it. And it was one of those things that, well, no, that'll never happen. You could do this and do that. That board doesn't have to worry. You don't have to worry about that and everything else. And we found this dead short, and it didn't take much vibration. It was like at 5 GRMS, and it failed quickly and brutally. It was just stunk up the lab. And they saw that and saw the hole burn through the trace, and they said, we got to fix that. They became believers real quick.
That's really dramatic and stuff like that. But when you get just a marginality, say like if I'd done the same thing and it wasn't a struck point, but the machine would quit operating at slightly above margin, slightly above the spec, and then one of them operated to 90 degrees C. I mean, if these weren't destruct, I would still say there's a wide distribution in your
Yeah.
variation, and you don't know exactly. And we did study it. We
And
looked at the collector, and this was a transistor switch, so we looked at the collector in, base. It was a bipolar, bipolar switch. And so we looked at the inputs and watched it as it's climbing in temperature because they wanted to see if they could figure it out. And we saw things shift slightly, with the pulses or whatever. But it didn't really matter. I just said because fortunately, and this is the thing, when you find something, you got to make an analysis of what could be done to increase that or increase the power. That sort of, instead of derating, doing going from 100 amp to 150 amp switch. Well, fortunately, the package dimensions and package layout and mounting was exactly the same for 150 amp. So, and they had already had that in the house on another model. Yeah. So we tried it, and so it was an easy thing to do. Whereas, they're not always. It may be a different package size or different, and you can't always do that. So that's another thing.
Yeah.
It takes.
It's got to be a solution that's feasible, and in the proving ground stage of this process. If you got a champion on the team that's saying, "Oh, we can put that together, we can get a part or two and give that a try," then you build a real credibility around the process. Is that look at the difference that happens when we swapped out this part, and it also comes with a good story.
Right.
I find it's got to be tied to what happens to the customer, what happens to your warranty, what happens to your brand it's going to cost a little bit more, but it's every one of those, like going from 5% to 0.5%. They probably still do HALT to this day.
Right.
Yeah. It's because it's huge at that point.
Well, but one of the more difficult challenges is when a company has a product already been fielded, they found some problems that might have been found in HALT, and they've already completed the corrective action and maybe put in a new redesign or a patch or something like that, and you say, well, we could have found that since they did thermal stressing or vibration or anything else. We could have probably found that issue, that low margin.
Yeah, then you need to recreate.
And they've already changed. They don't do that anymore because it didn't. They've already.
Well, what else can you find?
Right.
It's a matter then of, do you find something else that's really useful, and that's where. I don't know if you and I have butted heads on this. I don't think HALT's always the right thing to do. If you already got a long list of things and you got to go fix, well, go fix them.
Yeah. Well,
then go.
How did
HALT.
You find those things? That's what I find.
Well, your customers call. That's
right.
Like,
and whether those things been found. I mean, you're talking about fielding the product. The product's been fielded and out there, and you're getting warranty returns or getting feedback from the field. If you can, we had that covered, and that's the problem. Feedback from the field, as we had in a previous podcast, is very difficult sometimes to get. So, but if you've already got it fielded, that's different.
Or your first prototypes in the lab just don't work. Now you got plenty to work on. I had one director tell me, he says, "You want to do HALT? What do you want to do HALT for?" Because if you wait too much longer, and it's going to be really expensive to fix anything you find. He says, "I already have more stuff to fix than I can afford to fix right now. I don't need more things on the list."
Exactly. But, they did. And that's, at time zero, it doesn't work, or you're finding these combination of parts don't work without, you don't have to do any stress or anything. Okay. That's one condition.
I think the prototypes were made out of Legos and baling wire.
And that's not the time to do HALT. No, this is a very careful, on the timeline.
It was their last prototype. This is a real story. These guys were basically, they changed the design every day, and they kept pushing off when they locked the design down because they hadn't got anything to work yet. So they had no molded parts. They had no anything that resembled the final product. Just didn't. You'd look at it and go, "What is that?"
Right.
Kind of thing, and. If I told you what it was, you'd give it away. But it was, no wonder it doesn't work. you guys are just kind of jerry-rigging this thing together. And he says, resistor doesn't care whether it's here or there or the other place. It's, we're hand soldering all this stuff together, but we can't get the thing to function.
Yeah.
So it's supposed to do X, Y, Z,
Yeah,
and it ain't doing them.
You've got to have something working on the bench. All your samples kind of have to work. You may have one problem, but hopefully it's related to the assembly or something. And really, HALT
is something you
HALT,
know about, and you have a plan to deal with it.
You don't want to find assembly errors in HALT. You don't want to find things.
Well, how many times have you seen screws back out during HALT?
So
what? No, you guys thinking.
Right. So, whether that's a design for manufacturability issue or something, that might be something you address. But it's really hard because if you were to show some low margin, again, the engineers are likely to say it initially, it will never see that in its end-use environment. And they won't take cumulative fatigue over time or anything like that because they haven't seen it yet. It may take a year or 6 months to happen. Yep. So
those are tougher. You got to really understand.
Then you have to go back and say, okay, I told you so. If you'd found it in a HALT test trying to demonstrate the value of that, they might have dismissed it and then later found out it was very much a significant field problem. So those things.
Well, I had one client. You remind me of this one client. We were running HALT, and we were in the thermal cycling phase, and pretty much everything was doing well. And we got to the 100C swing, and we said, let's do some thermal cycling, see what happens. And it was looping a diagnostic package to check functionality and all these bits and pieces are working and so on. And the overall diagnostic took a couple of minutes, maybe 5 minutes to run. It checked this and then went over and checked that and did this, that, and other thing. And we went up to 100C or whatever the max was, and it ran it there for 10, 15 minutes, and it was like, it's fine. And we're heading down to 0 or I think minus 10 or something like that. And at 22C, it failed. And like, what? What was that?
22C.
Why did it turn off?
22C is 70 degrees Fahrenheit, isn't it?
I know. And it was a little bit warmer in the lab, so ambient was a little bit higher, or maybe it was lower. It wasn't exactly, and it was to that degree. When we went to 20C, it worked. When we opened the chamber up and had it at room temperature, it worked. And we ran it for 10, 15, 20 minutes, and it worked. And we said, we can't replicate it. All right, whatever. We didn't know it was 22C that was the trigger. We put it back in the chamber and started lowering it down, and we came back up and it failed again. And it was like, what? And so we zeroed in on that temperature and we could replicate it at 22C.
But it would go operate.
If we were at 25C, it wasn't doing 20C, it was working. And it had to be a certain part of the diagnostic had to be right at that temperature. And so we could scan past it, but if it was checking memory and not checking this other part, it wouldn't trigger it. It would go on, and then it'd be a cooler temperature, and then it was happy. And so,
well, that's a very unique. I guess that's unique. A hole in the going down in temperature. In almost all cases, I've rarely seen that, and many times have said, let's go to what we already know is it hasn't been tested to. But we had the 22C where you had that one. That would be enough to say, let's get another sample.
Oh, yeah. No, we were there for 2 more days trying to sort it out, and they flew in one of their other main engineers.
22C that had that problem.
It was only there.
23C did. 22, 21.
20. Yeah, within the specs of our measurement system, 20 and 25, it was fine. 22, when we had, we had thermocouples on the board, and when it was at 22, it fell. And it was a timing issue that it just hit just the wrong sequences. And they had all kinds of wizardry set up to try to track this thing down, and they figured it out, and they added a capacitor and it went away.
Yeah.
It was one of those kind of things, but they were hook, line, and sinker. It wasn't their first rodeo. They believed HALT was right. And then any failure was a good failure. And then you've got them, right? Now they bought in. And they, said, no, we're going to sort this failure out. And so we spent quite a bit of time diagnosing that one and troubleshooting it, and to where we could replicate it. And then we could say, well, what could this possibly be? And they had schematics all over the place. It was a lot of fun. Right. But it was the weirdest one. I mean, they were like, we're sitting there as the temperature's going up in the high temperature steps, and he was like, oh, it's going to fail. It's at 60 C. Oh, there's no way I can do that. And it went 80 C and went 90 C. And he was sweating bullets. And I'm like, well, let's see. Let's see what happens. And it wasn't until we started swinging the temperature that we found something really interesting. Yeah.
And that's, that's kind of, that's something that I guess I haven't, mostly in the HALT, of course, at first it's single steps in one direction. And at the very end, maybe if you've established that you have pretty good margins on both sides and you reach kind of a fundamental limit of technology, then you start going ahead and nothing breaks. You go ahead and start swinging the temperature. But usually I'm more anxious to test subsequent samples or, another sample with the high step limit test before I start doing the swinging temperature. It really depends, again, if you have your own chamber internally or you're going out to a lab, you just really don't have the time in a lab, and it's quite expensive. But anyway, but it can be done. And I would recommend that you do thermal cycling, especially with high-speed electronics, that you can do skewing of the timings and maybe catch what you found is a timing issue. And I've written about that. I have a paper on my website how thermal stressing can slightly shift and skew the timings of chips, because at cold, like minus 10 or so, you're going to get a different parametric performance than you are at 40 exactly. Or 50. And I did a paper on that. I'd never published it, but it's available on my website. So it's a very difficult thing to prove HALT, either post design, and post fielding sometimes, and also before they've had the issue in the field, because then they'll say it's not going to occur because it'll never see those conditions.
And I think the proof part is getting over those hurdles. I think 2 hurdles is we don't do good failure analysis anyway. They may not phrase it that way. And so that's a problem. And don't bring us problems, bring us solutions, kind of thing. And then the other group is that, will it show us anything we don't know about?
Right.
And sometimes you're lucky on your very first experiment with it and sometimes not. But the idea is that it does have advantages, and there's a range of different ways you go about doing it. And it's starting with, let's just give it a try. What do it's going to cost us a sample or two, and it'll take us a couple of days. Right. Let's see what we can learn. Right. And work on it from there. But it really is a mindset problem. It's not a technical problem.
It's a mindset problem of that not thinking of variation in manufacturing, variation in the supply chain, variation in end-use environment, and
lack of margin.
And lack of margin, right. Design. And lack of margin. And you'd mentioned it, and I've dealt with this, is just dismissing and not doing proper failure analysis, just saying, oh, that's just infant mortality. We find it.
Yeah, that was a one-off. That was a one-off.
We find a component.
All 4 of them failed exactly the same way. Oh, that was just a one-off.
We've had 14 failures, or 15, or 20, and all of them are dead shorts. The chip is just blown, and that must be infant mortality. And I'm thinking, I don't think
you're going to ship it with this.
I don't think so. That's like throwing a bowling ball at a door. Some doors will withhold it, but eventually they're probably going to go through. So that's kind of what I felt about that, is that they probably have pretty strong ones. The components resist some kind of horrible voltage spike repeatedly, and eventually they'll die. And that's what happens.
Yep.
So,
Yeah, no, so it's, if you're listening to this and you're thinking about doing HALT, and hopefully you have, we've been talking about it for how long, Kirk? 8 years, 9 years, something like that.
2016 when you started.
Give it a shot, give it a try and make it work and win over the group and add a lot of value and all that other good stuff. But if you got questions about doing that or, particular issues you're running into with your team, let us know. Head over to ascendoverliability.com/go/SOR. And you can find a couple of ways to get in touch with us. There's also Kirk and I and the other hosts of the show are available through LinkedIn and our About pages. So, hey, Kirk, you going to go break something today?
Yeah, well, I don't know. Maybe I will.
All right. Yeah, hopefully it's not one of your appliances.
No.
Have a good time.
Yeah. All right. Talk to you soon, Fred.
Yeah, take care, Kirk. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.